Thank you, Utah, for the welcoming address. Let's move on with the opening remarks given by Professor Alex Pentland at the MIT Media Lab. He is the founder and director of the Human Dynamics Group and the Media Lab Entrepreneurship Program. Professor Pentland is a pioneer in organizational engineering, mobile information systems, and computational social science, and among the most cited computer scientists in the world. In 1994, he was named one of the 100 Americans likely to shape this century by Newsweek magazine, and in 2011, he was chosen as one of the world's top data scientists by Tim O'Reilly in the Forbes magazine.
Hi. Hello. Glad to be here. I'm going to talk to you about things that are related to entrepreneurship, things that are related to starting a company, but it's also MIT, so these are going to be computational things that come from computer science and the ability to actually build things. And the name of this area that I'm talking about is social physics. Social physics is a phrase that's 2 centuries old. So around the beginning of the 1800s, when chemistry was first becoming a science and physics was becoming very successful, people dreamed of having social sciences, the sciences of management, the sciences of marketing, the sciences of politics really become science. And of course, they had to give up pretty quickly because they didn't have the data to actually create that sort of science, nor did they have the mathematics to be able to do it. But today, and in fact, just recently, we have that sort of data and that sort of mathematics to be able to begin to understand how you can actually predict what will happen in human organizations. For me, this story happens almost 20 years ago. That's where it begins, where I began to create a race of cyborgs here at MIT. It was sort of funny. We had head-up displays that were very crude. We had PCs powered by motorcycle batteries and one-handed keyboards. But what it did is it let us look at the problems that you would have and the opportunities you would have when you had computation and you had data on your body all of the time. And this was the beginning of really investigating wearable computing, which has become very popular recently. And in fact, one of the people up there, the one second from the left, is the one that was a technical lead on Google Glass. And other people have built wearable technologies that you may use pretty regularly, actually. For me, one of the things I first learned as sort of a joke is that nobody normal would wear stuff like this. So I started a project with a design school in Paris that they called the Pentland project, where we tried to design what wearable computing would look like in the future. And this is one of the first designs. So this is 1995, before there was ever a cell phone. And you can see pretty clearly there's something that looks like an iPhone 6 there. It has a little display, fingerprint reader. There's a thing that looks just like Google Glass, well, maybe a little bit different. But the thing is that wearable technology is constrained by our social environment and by our bodies more than by the technology. So that was sort of interesting. But that's not the big important part about wearable computing. The big important part is that you have sensors on the body, that you know something about people now 24/7. It's hard to actually imagine, probably for many of the people in this room, there was a time when you couldn't reach out to other people. You had to physically go there. And now you can actually sense how they're moving through the accelerometer in their phone. As the wearable computing takes off, you'll be able to sense heartbeat and other sorts of things. It's really like this collective has begun to develop. And the implication of that is that you can now begin to build systems that include people as a core part of the system that you're modeling. So this is sort of a hard concept. We all have models of human behavior. You can get a PhD in social psychology, all that sort of stuff. But none of that's mathematical. None of it's like building a bridge. None of it's like designing a chip. And that's what's changing. You'll now be able to design organizations the way you design physical things. And the reason is very simple. It's not rocket science here. It's that we now have data off of people's bodies about how they talk to each other, tone of voice, pattern of interaction, things like that, which we never had before. And we have machine learning techniques that can capture that data and build predictive models for what sorts of patterns end up with good interactions and what sort of patterns ends up with bad interactions. So what we're capturing here is not the sort of stuff you normally think of, the strategies and language that runs through your head all of the time. These are our habits, our culture, the things that we all have in common, not the things that are free will. They're the things that we decide that we will do like everybody else does because that's the way that you get along. And the implications of being able to model that are profound. Let me give you a couple of examples. So this is very recent work. We looked at an area of 60,000 kilometers in Europe, and we compared what would happen if you wanted to predict peak energy production within that area over the next week. And of course, there are normal commercial opportunities for do that, and normal methods. And those are very important because the way you build power generation is very different in terms of its cost and pollution, depending on exactly what the peak energy is. And what we added was one other thing. We added data from cell phones. And so we could look at the patterns of communication, the patterns of movement of all of the people in that 60,000 kilometer area. And we were able to improve the prediction of weekly peak energy by a factor of 6. That means reduce the energy, the error by a factor of 6, by adding in factors that had to do with how humans changed their mobility, how the call patterns changed, and so on and so forth. So that's a huge thing in terms of cost savings for energy production. Or here's another one. The beginning of this year around in London, we had data about human mobility again from just aggregate call patterns. These are not individual patterns at all. This is how many people are using each cell tower. These are how many people are using the subway. And using that data, plus historical crime data, we were able to do a good job of predicting which city blocks, which town squares were likely to have an increase in crime. So it's not something about individual people, it's about the patterns of human action that are vary for many causes, but turn out to be predictable, at least on the 1 month time frame. And of course, being able to predict crime is a pretty interesting thing to be able to do. And we've since been able to do this in other interesting areas too. Or this is one that's a commercial spin-off. This is some work that we did a couple of years ago. We took a dorm here at MIT, gave everybody smartphones, and in return they let us look at their behavior for a period of a year. And we asked them every morning about how they were feeling. Did they have flu symptoms? Were they depressed? Did they have a hangover? Those sorts of things. And it turns out that people change their behavior very regularly depending on how they feel. So I can look at the output from your cell phone, not what you say, just when did you get up? How much did you go walking around? How fast did you walk? Did you call your close friends? Did you call your work friends? Those sorts of things. And from that, I can tell if you're coming down with a flu. I can tell if you're feeling depressed. I can tell if you had a little bit too much to drink last night. Sort of a check engine light for your body. It's when you behave differently than you normally behave in certain directions. It's because you're not feeling well in some way. You may not even be aware of it. And so what Ginger.io, which is the spin-off that we have for this, does is it solves a problem for hospital systems. A hospital system may have 10 million customers, if it's a very big hospital system. And out of those 10 million, you might have 50,000 people that are getting sick right this minute, but you don't know which ones are getting sick. You won't know as a hospital until they get so sick that they have to come into the emergency room or see a doctor. But if you could know that they were getting sick now, you could reach out to them and be much more effective in your medical care and save a ton of money. And that's what Ginger.io does, says, here's the 50,000 people you ought to give a phone call to because these are the people that are most likely to be sick. And that's a huge sort of thing. And as the chief technical officer of the US said, this could really save our health system because it makes demand specific to need. Pretty interesting thing. So I think that gives you an idea of the types of things that I'm talking about, where you can build models of human behavior from all of this pervasive computing, from cell phones, from credit cards, from transportation systems, into our societal systems and generate tremendous savings and tremendous improvements in efficiency. But you can actually go quite a bit further than that in various interesting ways. So one of the sorts of things you can do is that as you look at many such examples like this, you find that there are certain properties about human behavior that are not just unpatterned random behavior. So if you look at the way most systems are designed, you know, they do all this stuff about how the bridge works and the road system works, and then there's a white noise source in there, and that's the people, okay? So they're not modeling people as being anything more than undifferentiated white noise. But if you actually look at data like this, you discover that interactions are local, that people are indeed largely autonomous, so that they have state changes that depend on their previous state, et cetera, et cetera. And as you begin to get enough data, you can actually build models that work pretty well across a wide variety of situations. And you can build mathematical things, methods that work much better than normal machine learning because you're building in all this knowledge about human behavior. What does all this mean? Well, here's an example. This is another spin-off that's been very exciting in the Valley, where we're doing things like financial fraud. So you can use machine learning techniques to detect, for instance, fraud in Bitcoin networks. But to do that, you need to have a lot of training data. And of course, if they're good criminals, they're going to change what they do very rapidly. But so there's a problem. You can't catch these people. On the other hand, if you know something about how groups of people interact, just because they're human and it's the normal way for them to interact, it turns out that you can find these groups very, very quickly. And if you can find them quickly, you can catch them. So that's pretty interesting. You can also do things on the plus side, things that are, I think, quite interesting. So for instance, a couple years ago, together with Tom Malone, who's over in the Sloan School, people at CMU, people at Harvard, we grabbed people off the streets of Cambridge, formed them into groups, and had them solve a whole bunch of problems. And what we discovered was something really interesting is the performance of the group, when we did this sort of mathematical modeling, didn't depend hardly at all on the intelligence of the people in the group. It depended on the pattern of interaction between the people. So was everybody contributing relatively equally? In other words, was there a sort of mathematical diversity of ideas? Or to put it another way, what was the entropy of the contributions from the people? And so that a group that was like this had much lower performance than a group like this, where there was much more equal contributions from people, and people were much more engaged. So that matters in terms of designing groups and brainstorming and so forth. In fact, it accounts for about 40% of the variance. So if you think about that, I don't know how many of you are familiar with this, but you all know about IQ, and you know IQ is pretty important in performance. So this is as important as IQ, because that's also about 40% of the variance accounted for. So next time you're in a group, try and get everybody to contribute equally, because you're raising the IQ of your group. But there's some interesting things with this, too. So this is an example where we were able to look at decision-making across large numbers of people. So this is a social network called eToro. It's a financial trading network. So people buy and sell stocks. They do Forex, so they buy and sell currencies, gold, silver, things like that. But it's also a social network a little bit like Twitter, sort of a cross between Twitter and Facebook. So you and I will, send little tips back and forth. But importantly, I can see your trading. So I know that you're long on euros and short on dollars. I don't know how many dollars you have invested total, but I know that that's your strategy. And I can see your performance over the last couple months. So I say, hey, he's really hot. He's doing something good here. And so like on most social networks, you can do things like, I can say, well, I'm going to follow him. Except on eToro, that means something very special. What that means is I'm going to take 10% of my money, and I'm going to invest it the way he invests his money, automatically. I don't even have to look at it. I'm going to be just as smart as him just because I clicked that button. Okay? And so you can look at this pattern of social interaction on eToro. And now the question comes up, what pattern of social interaction gives you the best return on investment? What's the smartest way to concentrate strategies and ideas? And what you see here is a graph which is the density of the social network, which is to say how tightly interconnected are things. How many loops are there, for instance? Things like that. There's a technical definition. It's a big, long formula. And it goes from people who are isolated on one corner to people that are in this echo chamber where everybody's saying the same thing, everybody's following each other on the other end. And then the vertical axis is market-adjusted return on investment. Each dot is a couple of million people's trades for a whole day. So this is years worth of data for a couple million people. So it's not little data, it's big data. And what you see is that trying to invest your money by yourself is stupid. You will lose. Right? Because these are smart people from all over. There's a large China contingent, if you care. And as those people begin to follow other folks, they begin to make more money. And in fact, the return on investment relative to the baseline goes up 30%. Would you like to make 30% more money? Yeah, okay. But as it goes past a certain point, the return on investment goes down. And what's going on there? In fact, actually, what I'm not showing is in this echo chamber area, sometimes everybody gets wiped out completely because everybody's following the same ideas. Everybody is talking to each other about the same things. In fact, the place where you get the most return on investment is the place where you have the maximum diversity of strategies, where I follow a series of people who don't pay attention to each other at all. So if I have the most independent range of opinions, then I make the most money. And again, I mean, you maybe have heard things like this, but you haven't seen data from millions of people over years where you can actually calculate it as a formula. And in fact, actually, we have a trading fund that's based on this. And if I had this just one financial device as opposed to a whole range of devices, that little tuning curve gets very, very sharp. So you can call out the good trades really pretty amazingly. So that's what I mean by social physics, being able to look at the network of interactions, the normal human patterns of being influenced by other people, and being able to build larger systems that perform better by building that knowledge into the system. Here's some data which I think I put in because it's relevant, I think, to this conference. This is diversity of ideas and innovation. So what we did is we used Foursquare to be able to look at how many different communities was a community exposed to. In other words, if you live in a particular city, are there other cities in different parts of the world that your population interacts with a great deal? Okay, so it's not the number of interactions you have. It's, are you familiar with, do you get input from these diverse communities that you have around the world? So that's the x-axis. And as you get more and more diversity like that, in other words, you're better connected to the world, what happens is, well, the GDP goes up as a nice log-log function, number of patents goes up as a nice log-log function, and the number of startups goes up as a log-log function. That's pretty interesting. And it says some of the things that you know, and some of the things in the last graph, which is this, having lots of different ideas trumps almost everything because it gives you the combinations, the ability to create combinations that are new. So just something to take home It's a good reason to have a conference like this. And I'm going to end here with something that I've been doing just in the last couple months. A few months ago, the Secretary General of the UN asked me to be part of a group that's going to define what the UN is going to do for the next 15 years. Last 15 years, they've had these Millennium Development Goals. Now they're going to have a new 15-year horizon. And part of that was a commitment to big data. The idea is one of the learnings from the last 15 years is if you're going to cure poverty, if you're going to make populations healthy and things like that, you have to be able to measure what's happening. If you don't know what's happening, then you make up all sorts of crazy stories. All right? So what is going to happen is the UN and the General Assembly are going to commit all of the statistical offices in all of the countries to be able to use all of this sorts of new data sources I've just been showing you to make much more better, much prompt, more open estimates about poverty, about disease, about ethnic violence, and various other sorts of things, which I think is really interesting because this isn't going to be just the government doing this. The government can't do it alone. This is really an interesting opportunity for companies, because what the government is going to have to do is work with companies to get their data, cleanse it, standardize, aggregate it, to be able to show what's happening in each province or each city. And so the companies that form that connection between private companies and government are going to be pretty successful. And of course, if you're the company that knows what's going on, there are lots of other sort of opportunities for you. So it's worth Googling UN data revolution and just taking a look at it and see what's coming down the pike, because this is maybe the way that big data that's outside of the individual company is going to get started. And that's it. I have a book just came out. It's actually going to be in Chinese in about a month. I don't have a picture of the cover, unfortunately, but all you guys read English anyhow, so here you are. Thanks.